Welcome. Happy Saturday, data people. Very excited to be here. Let's see, sound check, looks good. Anyone out there, let me know how the audio volume is. On the chat, anyone out there? I always have to check on the music volume. Seems a little bit hard to get it right. Anyway, oh, that's what's wrong. My mic was not powered on. Okay, that should be a little bit better. Hey Scott, nice to see you. And glad to hear the music's good. Let me get started. My name is Carl Gold. I'm a data scientist in Silicon Valley, California. Oh yeah, this is a good mix. Actually, I've been thinking I should promote the mix that I use. I can show you real quick, and this is for everyone watching the stream. I just use good old no copyright music for Twitch, so it's easy to find on Spotify. Great for your streaming, and I'll give a shout out to Kike Varela Reguera, who created the mix. So I play music in all my streams, in case you haven't been with me before, and it's definitely one of the things that I enjoy. So glad I found some good copyright-free music to bring you all while I talk about data. So what am I here to talk about? We are here to talk about data science. And I talk about something called churn. I should also mention that at the start of every stream I say the same thing. So if you've watched these a lot, you might want to get a cup of coffee and come back in 5 minutes, because this is where I level set so everyone knows what am I talking about when I'm talking about churn. So churn is when subscribers, customers, or users quit your product or service, and it applies to all products with recurring revenue, whether it's paid subscription, in-app purchase, or ad-supported. And the origin of churn comes from a metric that's called the churn rate, which is the percent of customers that quit in a given time period, like a month or a year is typically how you measure it. But churn is not just a metric now, it's also a verb. So you can say the customer churned, or even I'm churning from Netflix because I decided to read more books this year. That's actually me, I'm a book reader. But I didn't churn from Netflix anyway. And churn is also a noun. So if you work at a subscription company or a SaaS company, software as a service, you might say make a churn report for last quarter. And that's churn speak if you're in the business. So why learn about churn? I say it's the most common data science problem because every product or service today has a churn problem because every product wants to keep their customers coming back. But there's a lot of special tricks for churn, which I will teach you if you check out my stream or the book. And this is also a great way to learn data science foundations. If you're new to data science, I teach at a beginner's level the techniques. You know, all you need to know is Python and SQL, and you can learn these techniques, and you'll see how to take raw data, transform it into actionable results for some company. What is Fighting Churn with Data? I'll just throw this shout out at the beginning. It's a book that I wrote. It came out recently. You can find it on my publisher, Manning.com's website. And if you do that, you can use this coupon here for 40% off. It's also on Amazon if you want to get free shipping. So the book is about my experience as chief data scientist at Zora, fighting churn for many companies that are on the Zora platform. What is Zora? Zora, as I said, is a platform, and it is what many subscription businesses use to manage their customers and products. So you can see here Zoom, everyone knows Zoom right now. Zoom also became a noun and a verb this year because we're all on Zoom calls all the time, for better or worse. I don't know. It is what it is, but Zoom is now a noun and a verb, and they run their business on Zora, which means that if you make an account with Zoom, your account data is actually stored in Zora's secure data center. So it's a service that Zora provides to its customers. Zora also does your billing, and anyway, all these companies use Zora, and that's how I worked on a lot of different churn projects, because a typical data scientist works on churn at the company where they work, but I worked on churn for dozens of companies, and that's how I came to sort of systematize fighting churn with data. But what does fighting churn with data really mean? It's the cute phrase for the title of my book. What it really means is using data to drive churn reduction, because reducing churn is the purpose of everything that I do in the book and everything I talk about in this stream today. You can reduce churn by making a great product. It's always the best way. But you can use your data to figure out what are your most popular features without doing a survey, because surveys can be biased and they're also expensive to run. You can also do marketing to your customers, but this means engaging with customers who already are on your product and telling them about the best features that they're not using, because you want it to be really targeted. You don't just want to spam people. So that's where, of course, the data comes in. And you've got customer success and support, helping your customers, and sales and pricing. So you want to make a product with a 3-tier plan, like a standard, best and premier plans, or basic, standard, premier, whatever you call it. We call it a good, better, best pricing plan in the business. And you want to use your data to make a plan like that suits your customers' needs, but you don't want to give discounts to get people to not churn. All right, I think I have marathon or sprint talked through all the basic intro about what is churn and fighting churn with data. So I think I'm ready to get into some of the actual data, which is the fun part of this stream. So where is the data? Let's see, I'm gonna I haven't launched my Postgres connection yet. I will do that right now and get it live for you. So we're gonna look at some, whoops. That's the instructions. Well, you can show this now. This is how you get all this data. You can clone the repo from my GitHub site, you install Postgres and Python, and then you run a simulation. Because I don't actually give real company data to teach fighting churn with data, because real company data for churn is actually sensitive private data for the companies that possess it. It's the heart of their business. So if you can find a company who will give away their data for us to analyze churn in an educational context, please let me know, because I would definitely like to use their data. But so here we have a simulated data set that consists of a few elements. The first part is subscriptions, and this is an example from the subscription table. They're basic coterminal subscriptions. Coterminal means that the end date of one subscription lines up with the start date of another. So each subscription term is 1 month in these subscriptions. And you can see there's an account ID. Hope you probably can't read it actually in the stream, but this column that I'm pointing to has the account ID. You can see that account 1 started on January 30th, 2020, and their last date on the service was May 29th, 2020. And they had these 4 1-month subscriptions, all for $9.99. Now in this simple simulation, they're actually all for $9.99. So we don't do different pricing. But what we do actually also simulate is the behavior of the customers, which is actually kind of more interesting. So the behavior is captured by events. Maybe I can show you some of the events right here. First I'm going to do this set search path statement. I just walked back through my history there. If I set the search path here, this is a Postgres thing, I won't have to continually specify the schema that we're running on. So after I've set my search path, we can look at some events. And this is some events from the event table. And you can see they all have a timestamp. The first column is the account ID. So every event in this framework is tied to the account. So you do need to be able to track your accounts across sessions to use these techniques. And then the third column is a type ID. The type ID tells you what type of event it is. Now we can't see the event types here because it's just an integer lookup, but I have another query, I believe. I just saw it in the scroll back. Let's see, maybe I don't. Well, let's do that query. So there's an event type table, so I'm going to join on that. Event E, inner join, event type. I believe there's an event type table on E dot. So there's an event type column equals, let's see, think I need the event type ID here. Let's see if this query works. Just doing it kind of fast, but yeah, so now I'm joining on the type table, and you can see that these events are actually events of people using a social network. So there are likes, ad views, more likes. There's also messaging and replying in a message thread, and a few other events. So these are all the things that people do on a made-up social network that I've simulated. And these customers use the product and eventually they churn. And basically in the stream and in the book, we're analyzing these simulated customers for their behavior. And as you'll see, it's actually very realistic. It's very realistic. So let me get back to the talk track here. This is still kind of the background, and if you've seen my streams before, you know all that too. But if this is your first time watching it live, or maybe on the video on demand later on, this is the background for you. We got to level set everyone. So here's how you can get all the code to follow along with everything that I'm doing. It's in my GitHub repo, Carl284K, Fight Churn. So you should clone it, of course. I use Postgres and Python. And there are complete instructions in the GitHub repo for how to set this up. And then you run a simulation to get those events and subscriptions that we were just looking at. So then we actually made a data set. So this is all in previous streams. And I'll show you the data set. Actually, that's actually a good idea. I'll just show you the data set. This is an overview of the data set first. So in the data set, we had a 4.1% churn rate, which is shown in this first row. This is a set of summary statistics of the data set, which is using a code listing from my book, listing 5.2. I'm not going to show you this one because it's pretty basic. We'll do some more interesting code in just a minute. But this is to show you the data set that we're working with. We have a metric measuring the number of events per month for the customers in each of these categories. So there's likes per month, and in this table you can see that 99% of customers have a like per month. The mean number or average number of likes per month is 95, and the maximum is 6,600. So someone's really liking a lot of stuff. Hey, Strawberry Jesus 11, crazy name. Love the Twitch names. Welcome to Data Science. Glad to have you here. I'm summarizing the data set that we're using to analyze customer churn. And to show you what the data set looks like, this is showing it in just Microsoft Excel, which can be a pretty convenient way to look at data if you have it on your local drive. So each row in the data set represents one customer on one particular date. And then we have a bunch of metrics of how they've been using the social network. Like per month, new friend per month, post per month, ad view per month, dislike per month. How many social networks have dislikes nowadays? I think no one really does dislikes anymore. You can only like things generally. But this simulated social network has dislikes. And we'll see how all of these are related to customer churn in just a few moments. So this is what the data set looks like if you've never seen a data set. I went over how we calculated these metrics and how we created this data set in previous streams. So I'm not going to really belabor it this stream. We're just going to be using the data set and analyzing the data set. That's probably enough to give you the overview and get on to the new stuff. The next thing we look at once we've got the data set is we look at how does the behaviors of the customers relate to customer churn, meaning canceling the product. And many people would think, because this is a data science stream, that I'm going to dive in and use some AI, or at least a regression. But actually, we're going to start just using some cool visualizations and analytics. And I throw up here my favorite quote from a scientist, which is from Ernest Rutherford, Nobel Prize 1908. And he said, "If you need to use statistics to understand your experiment, then you ought to have done a better experiment." Now, anyone who's a data scientist or a statistician is probably thinking, what the hell? That doesn't make any sense. Of course we need to use statistics to understand anything. But what I mean, and what I think Rutherford might have meant, is that if you do a clever experiment, you can read the results from a simple visualization. without using statistics, you can test a hypothesis in a very strong way. Now let's look at some examples. And first we'll look at examples from some real case studies that I did. This is an example of the relationship between churn and a customer metric for the company called Klipfolio, who I worked with for several years. Klipfolio is a BI tool, which is like a dashboard. So you can look at your customer metrics in this. And what you can see in this chart is that the more times customers edit their dashboard per month, the less they churn, because churn is on the y-axis here. And the number of times they edit their dashboard per month is on the x-axis. And oh my God, I think I'm crashing. Looks like I just crashed my chroma cam. You can't see me, but I'm still here. Good thing I didn't completely crash. Hold on. We will get video back in just a moment. And I apologize for the weirdness. Please, thank you, ChromaCam, for being kind of crappy on the Mac. Let's see, am I back? I did start ChromaCam. Let's see. Still working, technical difficulty here. Restarting ChromaCam. Still not working. Let me try something else. I can just go to my regular camera. Let's see. What the heck? No, that's not working. Sorry, people. Technical difficulties. Technical difficulties. Technical difficulties. This has never happened to me exactly like this before. How embarrassing. But I did start ChromaCam, dummy. Boy. Starting it again. Please be patient, people. I was just about to get to the good part of the stream, I hope. If this damn thing would let me. Alright, who's an expert on Streamlabs OBS? I need like a Streamlabs OBS doctor right now. Let's try this. Well, here's the real me just sitting in my chair without my fancy virtual background. Anyway, nice to see you guys again. I was here the whole time. This is not the slide we were up to. Oh yeah, this is what we were up to. Okay, so just kind of skipped on the metrics cohorts. I was telling you about this for Klipfolio. Let me take one more attempt to do my virtual background because I do think it looks better. Let's see, can it work? No, it's crashed. All right, we're going real background. At least I got something working. Anyway, carrying on with the data science, because this is about, data science, not about whether I have a fancy camera that will, give me a floating background or floating on a background. Anyway, so from a chart like this answers the question, do customers who use Klipfolio more churn less? Now, do we need statistics to make this point? Obviously not, because the customers who are using Klipfolio the most in this top cohort are churning at like 1/10 the rate of the bottom cohort that's not really using Klipfolio at all. Let's look at a few more examples. I love these examples of real customer case studies. This is Broadly, which is also a software as a service product that customers use to manage their online presence with reviews. And this shows the churn versus the number of reviews that customers get on the Broadly app. Or this is actually review updates. So that means someone goes back and updates their review. But anyway, the point is, you can also see here, the more reviews per month that a customer on Broadly gets, the lower they churn. And again, this answers the question is, does using Broadly, the product, reduce churn? Hey C-Films, welcome back. I'm doing pretty good, other than that my ChromaCam just crashed and I was like off camera for a minute just a few seconds ago. But we are good. And interested to hear how you're doing, and also where you're from. I always forget where people are dialing in from. I know Scott's from LA because I actually met him there, but Anyway, one more example of a metric cohort is from Versature, which is a voice over IP telco service, which is disrupting the telco market in Canada. I also analyzed churn with Versature. Oh, you're the From Earth guy. I remember actually. I remember you from saying that on an old stream. Anyway, this shows that the more calls customers make with Versature, the less they churn. The bottom cohort with basically no churn, no calls, this is calls per month on the telco, or the total call time actually. It's not calls per month, it's minutes of call time per month. So the customers not making calls are very highly likely to churn, but just a little bit of calls and they churn at a much lower rate, so that once you get down to the elbow here, you're about 1/4 of the churn rate of the bottom cohort. And that's a pretty standard result. So, do these things all look the same? They kind of all do. And if you ever do a metric cohort for your own product or service, you should definitely see a chart that looks like one of these. That the more people use your product or service, the less they churn. That's if the data is good. You could definitely have problems, with bad data. That you won't get charts that look like this. In fact, we looked at some examples last week. We looked at a problem where there were partners who don't pay for a product. And you have people who don't pay, they tend to behave a little bit differently. Well, anyway, let's look real quick at how to make these cohorts, because we haven't actually done any live coding yet. This is not a new piece of code, because I did this on previous streams, but we'll look at how I make those cohort plots. It's chapter 5, listing 1 from the book. And if you get the book code, it's divided into these folders for each chapter here. So this is Cohort Plot, chapter 5, listing 1. And I've already got a breakpoint set in it. So I will just, oh look, it looks like my run configuration is also set to 5.1, which I didn't really realize. 5.1 version 3, actually. I don't want to run a version. I just want to run the standard. So this is the program that comes with the book. Those parameters are for the program that comes with the book to run these code listings. And I showed how to use it all in a previous stream. So now I'm just going to run this one to show you how I do a cohort plot. I like working with data too, C-Films. That's why that's why it's my job and why I spend some time live streaming it. So in this function, the first thing we're going to do is load the data from a path. And like a good programmer, the first thing I do is check that the data is there. And then I use Pandas to load it. That's what my PD is. So if you're not that familiar with Python and data science, you might not have known that, but if you are a data science person, you almost always know what PD means, Pandas. So this loads my data into a data frame variable, which is the churn data. I'll prove that to you by trying to open it. Occasionally this crashes too, but I like to live dangerously. And I like to prove to you that the data really is a data frame. Nothing to show. This usually works. And it also shows off PyCharm's cool visualizer. So here we go, it worked. So PyCharm, which is the IDE, integrated development environment that I'm using, has a great tool for visualizing data frames. So here you can see the index is made from the account ID and the date of the observation. Is churn, the first column, is my outcome that we're going to be analyzing. And then these are all those metrics, like per month, new friend per month, post per month. So I've proved to you that that is the data frame, and I just loaded it. And then I'm going to form those metric cohorts. And the cohorts are groups that are in the different deciles, typically, like the bottom 10%, the next 10%. And this function I just called QCut actually finds the deciles. That's also a Pandas analytic function. So Pandas is doing the hard work for me of finding the cohorts and returning them in this groups variable, which is actually a series indicating the cohort membership. Then I use Pandas group by on the two variables, well, the metric that I'm plotting and the churn indicator, and that gives me the averages and the churn rates for each cohort. And then I just put them into another little data frame. So this essentially has the result of the cohort analysis. So this is post per month, and you can see as post per month increases, churn rate decreases. And that's nice heat map highlighting from the PyCharm viewer. And that's mostly how I do these cohort plots. I'm really just taking advantage of Pandas built-in analytics. And I'll just let this run out for you. Well, you can actually see it popped up in my own window. So now I actually make the chart by plotting those. And now you can see I got a curve that looks a lot like the curves from the real data sets. So this is from real data. Let's see, how do I just run out? Uh-oh, terminating. Uh-oh, crashing. That didn't go too well. I think actually the debugger does not play nicely with the graphing function. Fortunately, I have the cohort plots that result from this code prepared for you. Oh god, I gotta kill that thing. Something weird happening in my Python. Let's see. Waiting for something. Background task. Waiting for pass hasn't detached. Jeez. What do I have to do to kill that thing? No. Problems. Wait. Here, stop. That's what I want. Okay, I killed the damn thing. Let's look at the results that you're supposed to get. So that was listing 5.1, which is running the cohort plots. And this is an example of running the simulation cohort plots for the data set that you generate with the book. All right, so this shows that likes per month, the more likes per month, the less churn. On this chart, you can actually see the churn rate. Here it's like 10%, and it goes down to below 2% churn for those who make more than around 100 likes per month. Those people sure like things a lot. This one is for posts per month. Again, this is all from the simulated social network. And this is for ad views per month, which is interesting because you might think that people who view a lot of ads wouldn't be happy. But this actually shows that viewing ads is just something that happens with people who use the service a lot. So people who use the service a lot tend not to churn, and they tend to see a lot of ads. And we'll think about that more later. We're going to come back to that one. This is dislike per month, another one where you think that disliking is bad, but actually people who are on the service a lot just tend to dislike more stuff. So that's why more dislikes per month is also correlated with not churning. This is unfriends per month, and here's one actually where a lot of unfriends really will do something bad. The more unfriends you have, the more you churn from this service. What else we got here? A few more. Messages per month, reply per month, and lastly also account tenure, which is how long someone's been a customer. And here you can see that in this simulation, the peak of churn is around 50 days. And this is surprisingly realistic, actually, in that normally customers don't churn at the very beginning, but there's a peak in churn early on in their life cycle, and then they tend to churn less, which is partly just a survivor bias. Like if they've made it past 80, 90, 100 days, they probably really like it. So those are the cohorts for this data set. And we're about to get into some more new stuff. Well, I actually started much of this subject last week also, the relationship between behaviors. Did I point out my ODSC mug actually? Do you guys know ODSC? It's the Open Data Science Conference Series. It's a very cool conference series. Just want to throw that out there, and they're not paying me for this. Look, you can tell it's a data science conference because it's like AI and ML. Although I think it's like backwards because I flipped my camera around. Anyway, let's talk about the relationship between behaviors. What is it? It's when having a higher value on one metric or doing one behavior tends to be result or go along with having a high value on another metric or behavior. Now, why does that matter? Because, as you'll see in a moment, you're going to have a lot of customer metrics. Great newsletter. Scott, which newsletter are you talking about? Not quite sure. But what was I saying? Oh yeah, so you'll probably have a lot of customer metrics, and you're probably also going to see that a lot of them are correlated with each other. And I'll show you that in just a moment. And it's hard to prioritize if you have a lot of metrics which are all telling you the same thing. Or, well, if you have too many metrics, it's just hard to work with. And it's hard for the business people to work with too. Oh, the ODSC newsletter. Right, Scott's point. ODSC has a good newsletter. I'm trying to think, am I on it? I think I actually unsubscribed from their conferences because they kept sending me ads for conferences. It got to be a little bit much, to be honest. So we use correlation to look at the relationship between metrics. And correlation measures the consistency of the relationship between two behaviors. I'm going to show you the output of listing 6.1 right here. So this is from the book. Also, you can run it. This is showing you what a high correlation looks like, 0.98. This is still a high correlation, but less highly correlated. I'm going to basically walk down to lower and lower correlations to demonstrate what correlation looks like between two variables. So, as we were saying, this is a high value on one metric tends to go with a high value on the other metric. And this is actually from Broadly, because it's saying customer added and ask presented. Ask presented is when they ask a customer for a review. This is from Versature, local calls and domestic calls. These are metric scores, I should mention, which are measured on a normalized scale. This is even lower correlation, 0.57. Once you get down to correlations like 0.3, they don't even look that correlated. But it does get even lower than this. This is a correlation 0.18. I guess that's as low as I go. But so that's a demonstration of correlation. This is also all from last week's stream. So I'm kind of still doing review from last week's stream here. This is showing you what a simulated correlation matrix looks like. Well, this is a correlation matrix. It's not a simulated correlation matrix. It's the correlation matrix for the simulated data set. And this was done with listing 6.2. Maybe we'll look at this one in a sec. So this shows you the numerical correlation between each pair of metrics. It actually shows some of them twice because the correlation matrix is symmetric above and below the diagonal. And here we can see, for example, that ad views per month is moderately correlated with likes, new friends, and posts. And messages is very highly correlated with replies. So that's the 0.86 correlation between messages and replies. Let's take a quick look at calculating the correlation matrix. This is actually another case where I just rely on pandas to do all the work for me. So I'm teaching you some handy pandas data analysis. Already got a breakpoint in this one because I was running it last week. So this will show you how easy it is to calculate correlations with pandas. I almost don't even have to run this. It might even crash my computer or crash PyCharm again. But look, we load the data set and then you just call one function in pandas. Well, it's a function on the data frame itself, .core, and that gives you the correlation. Let's look at it here. It's probably going to look basically like what I was just showing you. So here you go. There's your correlation matrix in pandas. Super easy when your data is numerical data, all in a data frame. So pandas has so many, great tools and tricks like that. All right, so that was calculating the correlation matrix. Very easy. And we're going to get to some more interesting stuff now. Like, let's look at a real correlation matrix. This is from the Clipfolio case study. And Clipfolio, why did I need to re-index? Oh, in the code? Let's look it back. That is, why did I need to re-index? Looks like, what was I doing here? So I'm setting the index to the first two columns here. Why am I re-index? I'm sorting the columns. I actually am not remembering. I'm going to have to get back to you on that one. This could be one of those weird lines of code that we all make sometimes where I was doing it for something else and then it might not really be even needed. Should we debug it and try to see what it does? So this is my first data frame here. What the heck did the reindex do? It looks fine. Well, one thing I think I'm doing here is I might be dropping the churn. See, one thing you notice I'm doing here is I'm only taking, well, let's take a look. No, I kept the churn. I'm sorry, Scott. I am feeling like a failure because I can't remember what my own damn code does. Why did I re-index it? What did that do? I'm not sure. I'm gonna have to get back to you on that one. Thanks. Thanks for not holding me to it. Let's get on to the new stuff. So this is a real correlation matrix, which has many, many more metrics than the simulation. And this is why I talk about there being significant information overload when you do a real case study. There was something like 80 metrics in the Clipfolio case study. And now this next slide actually shows you the same correlation matrix, but I've reorganized it to show the groups of highly correlated metrics. So there's a kind of large group of medium to high correlation in the top left, and then these squares along the diagonal are groups of very highly correlated metrics, behaviors that really go together. And this actually shows you the interpretation of all these metrics in the Clipfolio dataset. So this big block in the top left are all the metrics about viewing and editing the dashboard. Then the next block is all the metrics related to templates. There's a gallery of templates in the Clipfolio product. The next block is all the metrics related to importing and configuring data sources. The next block is API calls, there's a block for orienting and refreshing. And so these are all groups of metrics which are very strongly related to each other, because when a customer does one, they're typically doing the other things as well. How did I group them like that? That is the subject of today's stream. Woo, you guessed the subject that I'm getting to. I grouped them using a clustering algorithm, which I will hopefully be teaching you or demonstrating and showing you in under 10 minutes. So we're getting to how we group them like that. Now it's very easy to group them in a small data set, but let me tell you more about this. So once you group them, I don't just group them to make a pretty correlation matrix, I actually average them together. So this is showing a cohort analysis where instead of using individual metrics, I average together all 28 metrics that are related to editing the dashboard. That was on this chart. So I averaged together 28 metrics and then did the cohort analysis. And then you see a really strong relationship to churn. So the people who have the top on this average have really, really low churn rate. And this is a much more information efficient way to show this to business people too. Just to say, customers who have a very high use of viewing and editing the dashboard have a much lower churn, rate. And that way you don't have to, deal with all the 28 metrics or, work with so many metrics. So that's where we're going. I said I averaged them together. Now I have to explain this now because this is going to get into how we form the groups too. So the groups are stored in a matrix called a loading matrix, which is illustrated here in the middle. That's the middle matrix. So this is a toy problem. Pretend this is our data set with 5 customers and 6 metrics. And we want to group together the first 3. I'm going to tell you how to find the groups later, just a few minutes. But pretend we know that we've got 3 metrics in one group and 2 metrics in another. In the matrix that encodes the groups, we put in these weights, 0.33, 0.33, so 1/3, 1/3, 1/3, And then for these two metrics, we put in weights 0.5, 0.5. So that's actually how you both show what the groups are and calculate the average. So the average is literally the multiplication together of these metrics and summing them up. Now, if you're already in data science or statistics or math or many science and technology subjects, you know that what I just described to you is actually matrix multiplication. Who knew that? Who knew this was where it was going? Of course, it's matrix multiplication. So you take the matrix of your metrics, shown here on the left, and you multiply it by that loading matrix that I just described. And that is actually how you calculate group averages. Now, why do we calculate the group averages with a loading matrix? Well, it's very efficient. You can average together all the metrics for all your groups in one multiplication operation, and it scales well to big data. So that's actually how you handle correlated metrics. And maybe we should look at that code too. Do I have a slide for that? Well, I think we'll look at the code to do the averaging in a second, but first this is an illustration of, again, why this is important and why it makes sense, because you have so many metrics in these big groups, it's just information overload, and it really doesn't make much sense to look at them separately when they're correlated. So this is what a real loading matrix would look like. It's stored with the metrics on the rows and the groups in the columns, which is convenient because there's many more metrics than groups. So this is an exercise in dimension reduction. We're going to reduce the dimension of the data set by combining together the correlated metrics. And this is also the right orientation for matrix multiplication. This is the similar grouping exercise for the simulation. I'll show you this and then we'll do the code for this. This shows that we're going to make group 1 from add view, like, and post, which have these pretty high correlations, and group 2 will be message and reply, and then the others are not part of groups. And this is the corresponding loading matrix. And after this, I'm going to show you how we come up with a loading matrix. But it's good to understand the matrix multiplication operation and the averaging first. So let's look at applying the loading matrix. Now I actually already have that loading matrix stored, and I'll show you how to create it in a minute. So we're going to go to listing 6.3, which is applying the grouping operation to a matrix, to a data set that we already have. So as usual, the first thing we'll do is load the data set. In this case, it's actually a data set of scores or normalized metrics. And so I load it here, and then I drop the churn column because, well, I'm going to put it back on later, but it doesn't become part of the groups. So this is pandas to drop one column, quite simple. So now I have the data which I'm going to group in a new variable. Next I load the loading matrix. Say that 10 times fast. Load the loading matrix. Load the loading matrix. Okay, not funny. Hey, Algebra 97, I like your name. Quick answer. If we have multicollinearity between 3 features, is dropping one of these features a good approach to data cleaning? Well, it depends what you mean. It could be. But if you have true multicollinearity, so Algebra 97 is talking about a related concept to what we're doing here, but it's a more advanced notion. So multicollinearity means, let's test me on this. Can I explain multicollinearity? It means that the sum of your columns gives you some of your other columns, which is basically saying one of your features is a function of some of your other features, and it has to be an exact relationship. So dropping the columns is one way. I'm actually teaching a different way of handling it, which is to average together the collinear columns, or the correlated columns, is what I'm more concerned with. In churn customer analysis, we don't generally have true multicollinearity. but you do have correlated metrics or correlated variables. I mean, if we go back here and look at these, like if you look at messaging and replying, they're highly correlated. They're not truly collinear. If the correlation between two metrics is 1, they are perfectly correlated and also therefore collinear. There's more complicated cases of collinearity, but I don't want to go into it right now. So I say actually group your correlated metrics together and then average them, and then you won't have too much collinearity all after that. So that's usually my approach. The other thing you could do, Algebra 97, is use a regression with a loss function. I like to use ridge regression myself, and ridge regression will automatically zero out some of your metrics, and it's also very resistant to multicollinearity, because multicollinearity is actually really only an issue with classic regression, like least squares regression. But if you use a more modern regression method like ridge regression or lasso regression, multicollinearity is not so bad. That's the way it is. Anyway, back to this code where we're actually going to apply the averaging operation. So I've loaded now the data set. You need to do a regression problem. Could be, well, look in my book. And answer Scott, yes, I normalized with z-scores. That's why I actually say this is the score data. I kind of glossed over that, and I went into it in gory details in previous streams. Oh, and you're welcome for the answer, Algebra 97. And so Scott Edwards, yes, you must turn them into scores before averaging. And I gloss over that in this stream. I explained it in detail in previous streams. I can prove to you their scores though. This is always fun. Here's the score data. If I look at this data set, you will see that these are scores. You can see that all the metrics are now, they contain both negative and positive values, all close to 0. And this is an important part in the process, which I probably really should have mentioned it. But thank you, Scott, for actually bringing it up. Because the truth is, averaging together different metrics actually doesn't make any sense, does it, right? Can you average together likes per month and posts per month? What does it mean? The average of likes and posts, they have different units. However, metric scores, because they're normalized, it actually makes sense to average them together. Because if someone's above average in liking, they have like 1 standard deviation in liking. And if they're above average in posting, they have 1 standard deviation, say a 1 in posting. You can average those together and you get a 1 standard deviation above average person. So it actually makes sense with normalized data to average, and it doesn't make much sense with unnormalized data. Like I said, went into gory details of normalizing in past streams, but I haven't done the averaging yet, because now I'm just about to load the loading matrix here. So loading mat now in its own little data frame, and you can prove to you that this is the loading matrix I just said we were going to use. So I've got 3 metrics averaged into one group, 2 metrics in another group, etc. And now I turn them into NumPy arrays because we're actually going to do the matrix multiplication right now. So this was the line. I used NumPy matrix multiplication. I had to turn both data sets into NumPy and D arrays to do the matrix multiplication. And now in the next line of code, I turn it right back into a Pandas data frame. Who does that? I find myself doing that pretty commonly. Turn it into NumPy, do some math, put it back in a data frame to make it easy to read and get your column labels. So now the data is grouped, and I just reattach the churn column to it. And in this code, I actually save it. I've really already saved this, so I'm actually just going to kill the script. Well, I can show you the group data first, real quick. And you'll see in the new group data, once again, using my Pandas view data frame, which almost always works and only crashes my computer about 1 in 20 times. Now I've got a metric group 1 and a metric group 2, which is where those old metrics used to be, and there are fewer columns. So I'm down to only 6 columns of metrics from like 9 or 10 before. So I didn't do too much grouping, but this is how you do it. It's just one simple matrix multiplication with NumPy, and that's how you get the metric groups. Let me kill that code because I've already actually done that one. And next, we are going to, I think, finally talk about how do you find metric groups. How do you find these metric groups? Now I'm actually going to go through several slides of talking, kind of like a mini explanation of the algorithm. The algorithm is a clustering algorithm. It's called hierarchical clustering, also called agglomerative clustering, which I'll say carefully. It's also called hierarchical agglomerative clustering. And what that all means is you group them together in a greedy fashion by finding the most correlated things first. So here I mention, again, this works on metric scores, not on unnormalized metrics. You just identify the 2 most correlated and you merge them. Now I can actually tell you, why did I explain all this about averaging metrics together in groups in a loading matrix before I told you how to find the groups? Isn't that kind of weird? I think it's weird to teach it this way, but I have to, because you need to know how to merge 2 metrics to understand this algorithm. If I told you you're going to merge 2 metrics without having shown you first, I don't know, it would have been uncool. So now you know what merging 2 metrics means, but you replace them with the average and recalculate the correlation. And then you just repeat that again and again until everything's grouped up. And there's as you group together the correlated metrics, there will be fewer and fewer high correlations in your correlation matrix. And that's how you'll end up with, eventually there won't be anything correlated left. So now let's look at a toy problem. Pretend that this on the left was your correlation matrix, and you find your most 2 highly correlated metrics are reading and replying to metrics. Suppose they have 0.93 correlation. Well, what we're going to do, are slides public? No, but this is all straight out of the book. So you can, if you want your own version of this, this is all in the book. These are exactly the charts and diagrams from my book. And of course you can always, I'll have this up on video on demand later. So let's see, what I was saying is, first step is to form your first loading matrix. You take read and reply, and I say, those are going to be my first group. So I put in the entries in the loading matrix to group together read and reply, like I showed you earlier in the stream. After doing that, I recalculate to a new correlation matrix. Read and reply are now together, so there's one less row and column in the correlation, and you'll see the correlation gets smaller as we go. Next, I find the next most correlated metric is logins in this toy problem. Logins is also correlated to read and reply, so I now adjust the loading matrix to have 3 metrics in the first group and give them 1/3, 1/3, 1/3 weights. And that's step 2. Next, I apply this loading matrix to the data, and I get a new correlation matrix shown here. Now you can see how the highly correlated elements in the data set are dropping out. You can see we started out with 1, 2, 3, 4 high correlations, which I would call these ones that are in dark orange and red. Next, we've only got 2 high correlations left. Now we've only got 1 high correlation left, and we're going to group those, send and write, by entering the 0.5, 0.5 in the third loading matrix. And after applying these to the data set, I'm down to this correlation matrix. I've got write and send grouped, read, reply, and login grouped, and that's what's here in my loading matrix. And then if I look at my correlation matrix, there's nothing correlated left. All the correlations have been merged together, all the high correlations, and only small correlations remain. So that's when the algorithm exits, and basically. Now that's actually how I explain the algorithm, and that's to give you the intuition behind the algorithm. You're actually going to see now that the code looks nothing like that because all the really interesting part is done in package functions. Is the threshold for entering group arbitrary? Yes, Strawberry Jesus 11. It's actually a parameter. Let's look at listing 6.4 from the book. I got too many tabs open here. So listing 6.4, which I've never demonstrated in this stream. Well, I might have in my old stream on the live book data set. But so let's see. This is multiple functions here. This is actually the most complicated listing in my book. This algorithm to find the metric groups and put the results into a loading matrix is the most complicated code in the entire book. So get ready. This is going to be super fun. This is the main function that you call find metric groups, and here I've got a threshold to answer a Strawberry Jesus 11 question. Here I'm using a group correlation threshold of 0.5, so it stops when there's no correlations above 0.5, or when all the correlations are below 0.5, it'll exit. And you can set that. You know, there's different reasons to set it. Typically you set it to a moderate level of correlation, like between 0.4 to 0.6 is usually the threshold that I use in finding these, although you can fine tune it in each case. So let's put a breakpoint here and we'll look at the entire algorithm. I need to make a new configuration because I have these separate configurations for each part of each listing. This will be my configuration for listing 6.4, blah, blah. Again, this is the parameters for the program that you can use to run the book listings. You can import these book listings into your own code or just run them, using the program that comes with the book. So let's go through the code for finding the metric groups in Python. So as usual, I will start by loading the scores into a data frame. So here it is. I've got my score data in a data frame. Instead of looking at the whole thing, can't you just look at the shape? It is 31,721 rows by 10 columns. And there's 9 metrics and 1 column for churn. Okay, so we drop the churn column. We'll reattach it later. I figure out what are the metric columns. And now we go into the first function, which is the most important one, where we find the correlated cluster groups. It's actually right up in this file. What did I do? Oh, I just went into the correlation function. That's not what I want. I want to go here. I'm calling the correlation function on the data set. I don't want to actually go into that. I'm going to go into find correlation clusters here. Now this is actually where all the magic happens in this, and it's a little bit of a letdown because I'm just going to use this function from SciPy. So here you can actually see I've got SciPy cluster hierarchy and SciPy spatial distance are the real packages that I'm going to do the work with. So the algorithm actually works in terms of dissimilarity, not similarity, and correlation is a measure of similarity. So the first thing I do is I flip my threshold into a dissimilarity threshold. Also in this case, my threshold was set to 0.65, and I set it that way because I wanted to use a relatively high threshold in this problem. I can explain more about why later. So the dissimilarity threshold then is going to be 0.35. So you turn similarity into dissimilarity just by subtracting it from 1. And you do the same thing for the correlation matrix. Somewhere. Yeah, well that was it. Is that you take 1 minus the correlation matrix. And that means that the most similar items have a 1 correlation. And then when you do 1 minus the correlation, they get a 0 for dissimilarity. The most dissimilar items in the correlation matrix have a -1 correlation, and those would go to a 2 dissimilarity. So that's how you do it'll be just the opposite. Thank you, Algebra 97, for letting me know someone's out there. It means a lot to streamers. So this is actually where we do the clustering. The linkage function forms a hierarchy of the relationships or correlations between the points. So this is actually where you're doing most of the correlation, but this doesn't actually find the groups. The hierarchy function finds the relationships, and this is really beyond the scope. So I gave you an intuition for what the algorithm is doing, but the execution is actually quite different. Next, we use fcluster to actually find the clusters, and that's really it. The labels list is a series of what cluster each metric was assigned to. So you can see that metrics, let's see, well, the first metric is in group 5, metrics 2 and 7 are get put in group 2. So this is just the labels. Now this actually did the grouping and clustering just by using the SciPy functions. And now the next part of this algorithm in this code is actually to make the loading matrix. So we basically need to figure out, we want to get a nice looking loading matrix like the ones you saw before from the clusters, which are actually not that helpful. So I think I'm going to skip this subfunction. What this does is it actually relabels the clusters so that the cluster with the most metrics is number 1. The original algorithm doesn't even do that for you. Let's see, this is a dictionary of the counts in each group. So group 0 has 3 metrics, group 1 has 2 metrics, and the others all have 1. And this is the relabeled data set. And I do that because the output of the hierarchy and clustering functions, they're just in random order. But I always want the group with the most metrics to be first, as I showed in the correlation matrices earlier. It's just easier to read if you put the largest group of metrics first. So I do that reordering. The next thing I do is make the loading matrix itself. Let's go into this one. So here I actually create an empty matrix for the loading matrix, and it has to be, the dimension has to be the number of original metrics by the number of grouped metrics. And then in this loop, I'm basically going to go through and fill in the values of the loading matrix by looking them up in the data that I've collected. I'm not going to go into all the details of this algorithm too, either. But this is just basically what you have to do to take the result of the hierarchical clustering algorithm in SciPy and turn it into the result that we need. So let's see. The rest of this is really just doing renaming the things. So now I've made my loading matrix in the data frame. This was as promised. Still out of order though, so I've still got to actually resort it, because so you see there's a lot of little mechanics that go into getting the nicely organized loading matrix that you end up with. So now I'm doing the sorting. This is using the data frame sort values, and I have to put in the order that I want for the columns. So I wanted most of them to be in descending order, but the one with the correlations in the ascending order. So now my loading matrix is going to look like, I think it'll look like it's supposed to. Here we go. So now we've actually got the loading matrix. Hey, Maddie Two Shoes. Wait, good morning. For you, it's good morning because it's 1 a.m. or something, but thanks for joining the stream. Hopefully you've been having more fun on your Saturday night. And this is just your nightcap. Anyway, so this is the loading matrix that we just created, and I finally reorganized it into the order that we want. So now we've got the loading matrix, finally. And this returns it. And that's actually really it. Then I just save it out. So now I've saved the loading matrix that we've been creating all this time. And I can go briefly and show you, prove that we just created the loading matrix here on my hard drive. Let's see, I gotta sort these by the modification date. All right, so here's the loading matrix that we just saved. Where is it? It's hiding. Hey, thanks for the subscription, Scott Edwards. Wow, an actual subscriber. Why did we do sort order equals false? Okay, because I wanted to sort descending by everything except the last thing. Let me go back to that little bit of the code for Algebra 97's question. Let's see. When I was doing the sorting, I was up here, right? So this sort order will mean that, let's see. So I was going descending. I think, why did I do the last one not descending? I have to look at what the columns were. Should I step through it again? So most of the columns, I think these are the weights at this point. Why did I do the last one ascending? Yeah, it's the ascending sort order. So this making false times the number of rows in the loading matrix. And then I set the last one to true. So I'm sorting them all by descending. Now, why did I do the last one ascending? I'm actually having a little bit of a hard time remembering this. Probably because if I look at this right, I'm gonna have to go back and look at it again. I mean, this is the order that we wanted. So these ones are supposed to be descending because I want the grouped metrics on top. I'm trying to remember what the ascending part was. Let's look at this again. I hate unanswered questions, and I like running code. Let's go to that. Go to that next breakpoint. To the next breakpoint, I guess. Here we go. So what have we got here in this loading matrix? So the loading matrix at this point looks like this. So it's out of order. Oh, and the last column is actually the name. That's why I did the last one in ascending order. I'm not crazy. I descended all the features except the last one, which is the name. That is my last trick. And then I dropped the name. So I probably attached the name for that purpose. And then I probably drop it later. Yeah, then I drop the name column. That's why I did it. And why do I want to, so they're sorted in ascending order by the numbers so that, this group comes first and then this group. And then I sort them by the name in ascending order so that within each group, they're alphabetized. God, well, shows what happens to everyone. I wrote this code more than a year ago. God, it's like, when did I write the code for this chapter? It's probably approximately a year ago, maybe more, maybe like 13 or 14 months ago. And now you're asking me, why did I sort the last one by ascending? I couldn't even remember that I had to do that to get within each group they're alphabetized. But that's what I like to do just to keep things organized and easy to read. So now we have beat to death, I think, this algorithm. And we can do another one, which is cool, which is ordering the correlation matrix. So now, how do I create those ordered correlation matrices? Yeah, especially a lot of time has passed in the last 13 months, or if you just think of the last, 10 months, really, since COVID and everything, the world started going crazy. It's hard to remember anything. So to make the ordered correlation matrices, I'll show you right now. This is actually really easy. This is how we do an ordered correlation matrix, which is listing 6.5. I can show you very quickly. Whoop. Oh, I didn't set a breakpoint. I wanted to show it to you, but this is listing 6.5, which is after you've done the grouping. Then I make those kind of pretty ordered correlation matrices. Oh no, I still didn't set a breakpoint. Quick. Too slow. Well, it's such an easy listing. I don't even know. This is going to be real quick. You load the data, and I load my loading matrix. And I already went through all that hard work, too, which we were just talking about, to sort my loading matrix into this very particular order. So I've got my group 1 on top, and then alphabetized within the group, and then my next group, alphabetized within the group. So now if I want to reorder my data set to that order, it's very easy. I load my data set and I just reorder it with this one-liner by putting in the index values. Well, I should make it clear. The index values in the loading matrix are the names of the metrics. So these are my metrics. Ad view per month, like per month, post per month, message per month, etc. And now I'm going to reorder the data set columns to the same order as the rows of the loading matrix. And it's as easy as that. And then I take my correlation and then I just save it. So that is how you, after doing this exercise, ooh, cool emote, Scott. Oh, is that like the world burning or like the Capitol burning? Oh wow, what a year it's been. But hey, shelter in place got me to take up streaming, so if it weren't for the pandemic, I wouldn't be talking to you right now. So you got to focus on the positive, right? I think a lot of people have taken up streaming because of the pandemic. I'm in good company. So from that listing, I just saved my ordered correlation matrix. I don't know if you can read the little type here, but I'll open it up real quick and then pull it over. I'll open it up real quick. This shows you the ordered correlation matrix that I just saved. Doesn't look so hot like this, but just got to do the heat map. Apply the heat map, and hey, lo and behold, this now looks like the ordered correlation matrix that I was talking about. And now it's passably readable, probably even on your screen. All right, now we've got an ordered correlation matrix. We've got a loading matrix. The last thing I'm going to talk about is comparing this to other forms of dimension reduction. Hey, Maddie. Oh, you also took up streaming because of being at home. It was basically like, I need a new hobby. I guess I also took up streaming because of writing the book. I have to give credit to my publisher, Manning Publications. This is the book in Manning Publications. They were the ones who first approached me and were like, hey, do you want to live stream on our channel? And now, got me hooked. I also realized it's a great way to teach people about my book. Now, let's talk about hierarchical clustering versus principal component analysis. Do we ship your book to Macedonia, Europe? Algebra 97, I am pretty sure the answer is yes, because for one thing, you can get the ebook. If you go to manning.com, definitely get the discount code. I showed it earlier in the stream, and I'll show it again at the end. There's a 40% discount code. And manning.com, you can get an ebook. You can get Kindle, PDF, or whatever. And I'm pretty sure they'll ship it. They do a lot of international business. So, for those of you who don't know, now I'm going to talk about principal component analysis and compare it to hierarchical clustering. Because probably most people learn principal component analysis for dimension reduction if you study statistics. And you might wonder, how is what I did with hierarchical clustering, how does it relate to PCA? And you can see right here. Now, if you haven't heard of PCA, I'm actually not going to explain it in this stream. It's a long topic. For those of you who already know data science, PCA does the same idea as hierarchical clustering, where you're going to form a loading matrix which will reduce the dimension of your data with a matrix multiplication, but it uses a completely different algorithm. And that algorithm has a lot of nice statistical properties. I say here it's statistically optimal. That's actually, that doesn't mean anything. For statisticians, what it means, they talk about, it captures the maximal information for a given number of remaining dimensions after the reduction. But the problem with PCA is it's very hard to interpret, and I'll tell that to you right here. If you compare, on the left here, this is my loading matrix for Clipfolio from hierarchical clustering. And you can see clearly all the metrics that form a group have a positive weight together, and all the metrics not in that group get zeros. So it's pretty easy to interpret what your groups are, what's in a group. You know what your groups mean. It means there's an average of these weights. In the principal component analysis, I reorganized it so it's in the same order as the hierarchical clustering loading matrix. And then you can actually see that the same groups are highlighted. The same groups get similar weights. The left chart, it actually is created from a dendrogram, Matty Two Shoes. Were you here when I went through the algorithm? It was earlier in this stream, and we actually used linkage and f-cluster and scipy, which is basically the algorithm of a dendrogram. It's a hierarchical clustering. I don't know. That's what I learned to call it. So PCA, it has the same basic groups as the hierarchical clustering, but it also has a lot of, Algebra 97 confirmed. Yes, hierarchical clustering creates dendrograms. Maddie, in the way I taught it, go back and watch the earlier part of the stream when you have some free time, during the week. I teach a really intuitive way of understanding it. I don't actually teach you the real hierarchical algorithm. I teach you a hand-waving version of this is what it does, and then I show you the code. That's kind of the way my book works. Anyway, PCA adds a lot of small weights on these other things. Like if you look at these ones, it's like 0.03, 0.05, really small weights. And it also adds negative weights. And those make it a lot harder for people to understand. Because in the hierarchical clustering, the first component is the average of these metrics, 1 to 28. In PCA, the first component is the average of everything. And they all just have these different weights. And you're like, what? The average of everything? And then the next component actually has negative weights. And negative weights in an average is very hard to explain to business people. So has anyone worked on this and tried to explain PCA to business people? It is not pretty. Do not try to explain PCA to business people. And that's really why I started using hierarchical clustering for churn. Because I've always got to explain these results to people who work at companies, right? People in the business. And you can tell them that you made an average score, and that's fine. They're like, okay, it's an average of the scores. But if you tell them that my average includes negative weights, then they're like, what? It just doesn't make sense. And you can really do just as well with this kind of analysis. PCA has more information, and the negative weights are actually useful for contrasting metrics. But I have other techniques to get the same result, which I'm going to go into next week. So that's why I don't use PCA, just because it focuses on the same groups. So the broad outline of PCA is the same. Like if you look at this second component in PCA, it's the same 7 metrics emphasized in the second component of hierarchical clustering. But then it's got all this other stuff. This isn't actually about Strawberry Jesus 11 for your question. This isn't really about negative influence. This is about negative weights in an average. Now, for something to be an average, the weights need to sum up to 1, basically. But it gets pretty unintuitive when you make an average by having negative weights on some metrics and positive weights on other metrics. That's not really an average, that's a difference. If you use negative weights, then you're actually forming differences between the metrics. But there are more intuitive ways to explain the differences between metrics, and we'll get to that actually in next week's stream. But the next thing I want to do is I actually want to do a live hack, because in my book I don't do PCA. So I'm going to live hack to do a PCA function on the simulated data set that we were just looking at. And so I can do this result for you. I didn't actually do this in the book. I'm actually going to make a new function right now that will do PCA on the simulation data set. And then we can see how it works there. So to make my new function, I'm going to do what every good person does, or every smart person, which is I'm going to copy something from my old function, which is I want to reuse the first part of my finding metric groups function for the hierarchical clustering. I'm going to use it for my PCA clustering, or it's not clustering, it's PCA dimension reduction. So let's see. First I'm going to add a new function, and I'm just going to call this one listing 66. But yeah, you could use the absolute values of the PCA, but then it doesn't mean the same thing. Those negatives are there for a reason. So actually, I don't think you can do that. I'm pretty sure that's not like a proper technique to just take the absolute value of the PCA loading matrix. I mean, if anyone who knows more math than me can correct me on that one, but I think those negative weights have to be in there or it doesn't work out right. So my listing 66, I'm going to call it PCA groups. How about that? .py. That's going to be my new function. And like I said, I'm going to copy from my old function to make it easier. I want to copy all this part where I load the scores. Maybe I'll need this too. So I'm going to copy all this into my new function. I'll probably have to copy some of my imports as well, of course. So I need OS and pandas for this to work. And who knows, maybe I'll need NumPy. I'm not actually sure. I don't think so. So I don't need this threshold, but when you do principal component analysis, you need the number of dimensions. And I'll need that in just a few minutes. So the next thing I need to do is remember for myself, what is the Python function for principal component analysis? Does anyone know? Uh-oh, music is lagging. Oh, Strawberry Jesus agrees. Yeah, you can't do it. Yeah, you can't take absolute values. PCA. How's the music now, everyone? I actually hear it fine. And it's some dance music for data science. Why does data science go good with dance music? I don't know. Anyway, I need to find out what's the Python function for PCA, because I don't have stuff like that memorized in my brain. This is my website if you haven't seen it. Fighting Churn With Data. PCA, sklearn decomposition. Ooh, someone knows. I'm just going to look it up too. You're probably right. Algebra 97, I am not doubting you. I am just going to look it up here. You were right. sklearn decomposition. So I need to give the music is stuttering. Is the music stuttering for everyone? Maybe I should turn down the volume. That must be really annoying if the music is stuttering. Alright, I just turned the music down a bunch. Is it okay now? Uh-oh, it's stuttering for everyone. Shoot. That will turn the music off. I wonder if I can just turn it back on and start it again. I actually can see it. I can see it. Yeah, I can see it's screwing up. All right, we're going to do the rest of the stream without music. That really pains me. Yeah, or I'm going to turn it way down. I don't know what's wrong with it. Should I just kill the music? Not too much left of this stream anyway. I'll try music again in the end. Let's finish this algorithm. Maybe I need some silence to really concentrate on my coding now. So, okay, so I need to import sklearn decomposition, PCA. let's see. From sklearn, composition, import PCA. And that should be a good start. And let's look back at this documentation again. Remind myself how this works. So you create it. Here, I'll make the font bigger so you guys can all see this. So create it with a number of components. Attributes, and I think you call like a fit function after you create it. Examples. Here we go. Here's the example. Create it and then call fit. There you go. That's what we're going to do. I'm just going to copy this example. PCA equals PCA. Here I'm going to use my number of components. Well, I called it number of dimensions. PCA.fit, and we just pass in the score data. Boy, it is hard to stream without music. It is just so much better with music. But it was pretty weird before. I don't want to hurt your eardrums. Okay, so I call PCA.fit, and then I probably just want to look at the components. Pretty sure there's like a components variable. Oh yeah, here we go, components underscore. So that's what we're going to want to look at afterwards. Equals PCA dot components. And I think I'm just going to save this out just to make it simple, and then we can look at it. So I want to look at how I save I want to copy my code here for how I save the loading matrix. It'll just make it easier. By making a little save path. I'm going to copy this part. So as everyone knows, it's always easier to copy paste old code. But don't forget to modify. My first boss at a programming job out of college told me, copy and pasting as code is good, but don't forget to modify. Copy, paste, and modify. So let's see. And I almost want to try the music again. I think it's actually better now. In my meters, it looks like the music is not studying. Yeah, copying and pasting code is like a skill nowadays. So let me know if the music's messed up again. I got it back on. But the key is to remember to copy, paste, and then modify. So I want to change this to, I'm going to call this my PCA components, whatever. And then I'm just going to, let's see. You know what I think I need to do is make a data frame. I need to make a data frame from the PCA components. Okay, let's try this. We can fix it up later if this isn't good. The next thing I need to do is register this function in the framework, the code framework for the book, by entering a configuration for it in the JSON file that configures the code. Whoops. So if you haven't dug too deep into this code, this will be new to you. But basically, there is a JSON which configures how all the listings are run. And that's where you can set variables for them. So in Chapter 6, I have these entries for different listings. I need to make a new one. Let's see. This is probably a good example. Yeah, because it has parameters. So I'm going to make a new entry in this JSON for listing 6, and this is basically going to register my new function. So I've got to change this to listing 6. So the keys are unique. A strawberry Jesus 11. For you to understand, negative coefficients in PCA represent linear dependence. So let's say you're looking at how being skinny influences your chances of survival in post-apocalyptic world. Oh, that'll be fun. You can't take absolute value and turn it around. Let's see, what I understand about the negative values in principal components, I mean, principal components is supposed to be finding directions of maximal variation And what I think negative weights means is that if a variable is that aligned maximal direction basically means correlated. So it's looking for the direction that is shared between those dimensions. And if you have a negative weight in your PCA matrix, I think it means that if you turn a metric around, then it's more aligned. But anyway, it's kind of hard to interpret that stuff. All right, but I'm doing my new function here. So listing 6, the name for it is PCA groups. My parameter is no longer group correlation thresh. I think it was n dimension. And I actually want to set n dimension to the same as I got in my other loading matrix, which was 1, 2, 3, 4, 5, 6. So I'm going to do 6 dimensions to make this comparable. Whoops. And that's it. So now my new function is registered in this framework for the book, and I can run it using in this way, hopefully, if I haven't screwed anything up. Let's go, I'll make a new configuration for running it, which will be 6.6. And the last thing I need, interpreting the PCA is like speaking the language of the gods. Yeah, PCA is really hard to explain and interpret. And like I said earlier, that's why I use hierarchical clustering if I need to work with business people. Or honestly, if I need to work with it myself, if I want to understand it. I will use a hierarchical clustering to understand the groups, and then a PCA, maybe, if I want to do something more advanced. But I use the HC for my understanding. So I think we're good to try running this. Metric columns. You know what I should do actually? No, this is going to be even better. I'm going to say I should use the names of the metric columns as the index here. And then I'll really run it. How's the music for everyone else now? I'm hearing it and it sounds pretty good. Hopefully the stuttering is gone. So let's debug this function. And is it working? Am I in the debugger? Could not find listing 6.6 PCA groups. Okay. Oh, I didn't remember copy, paste, and modify. Wait, this is 4.4. Yeah, this is supposed to be PCA groups. Remember how I copied that from the other file at the very beginning? So copy, paste, but don't forget to modify. Yeah, hierarchical clustering, I got it in SciPy. I'll just real quick answer Strawberry Jesus 11's question. If I show you, if you saw before my implementation of hierarchical clustering here, I was using these functions, SciPy cluster and SciPy spatial distance, so a utility, but it's mostly SciPy cluster and hierarchy. So pretty easy to remember. And as I demonstrated in my own listing, you might have to do some work to turn the output of those functions into what you want exactly, depending on what exactly you want. In my case, I wanted a loading matrix, and that took some effort. So here is my attempt at PCA that I just wrote up. I loaded my scores. I'll just check real quickly. Score data dot shape. And it's my good old data. And okay, I dropped the churn column. These are my metric columns. Now I make the PCA object here, and this should actually do it. So now I'm going to call my PCA fit function. Seems to have gone fine. Now I have a PCA object here with n component 6. So it looks like it worked. And this should be my component array right here. All right, well that should be it. Oh, you know what? I think I need to take the transpose. This is actually going to crash. Want to watch me crash? I'm pretty sure this is going to crash because I wanted to have the metrics in the rows, which is why I put the index. I think this is going to give me an error. Ready? Yeah. All right, I screwed it up. Bug number one, but we can easily fix that by taking the transpose, which I think is like T or something. How do you take the transpose of one of these? Let's try that. You stream on random days at random times, or like tend to do stats more, or at this point, I'm going to go over my schedule at the end of the stream. I basically am only streaming Saturdays now. I have a day job, it's a full-time job, so during the week, streaming, not really for me. I also got a family, stuff like that. So, okay, yeah, T or NP transpose, thank you. But yeah, so I do this Saturday afternoons. It's Saturday afternoon my time, depending on, what time zone you're in. It could be late for you, like Matty Two Shoes, who stopped by to say hi, probably before he went to sleep. Let's see. So here, I think I'm really going to get this to work. Going through the code that we just went through again. Now here's my components. I'm just going to just double check this. .t, yeah, okay, that'll do it. Now this should work. Okay, yes. So now my components are in a little data frame that should have names on the rows. So, interesting. All right, it's kind of taking shape. I actually haven't really done this before. So now I've got my components, and now I'm just going to save them. Let's see. It says it's going to save them. Should say that. All right, so it should have saved them to my little output directory next to where my other ones are. So that was a pretty good quick live hack. Let's see the result. So now here's the PCA components. We're going to want to put them like side by side. Problem will actually be the sorting. I should have sorted them. Let's see. Here I've got my new, this is my new PCA loading matrix that I just got out of my function. And we can add the highlighting, which makes it a lot easier to read. And now, let's see, I want to do that comparison like I showed you in the slide earlier. Unfortunately, these are all in like a different, the metrics are in a different order right now. So what I need to do, let's see, I can probably just order them real quick by hand. Let's see. Count tenure. Needs to move down. There's probably a better way to do this. I can do it with like a VLOOKUP. But that won't be so good. Let's see. Well, I wanted to show you how these are similar, but it's like I need to get add view, then like. All right, let's just get them in order real fast. Then post. I'm just going to move these into the same order as the other loading matrix, hopefully quickly without screwing anything up. Message and then reply. Well, that's probably enough to show you. You can now see kind of the main result here, that how PCA and the hierarchical clustering give you very similar results. Let me put a little highlight on this one too. Then it'll be really easy to read out. So you can see that the hierarchical clustering and the principal component analysis both put these add view, like per month, post per month with high positive weights. These ones are also pretty correlated, and I could have clustered those together with the first three. I kind of decided not to just to make more groups. I could take sorting code from the other place, But I need this order. That was the thing. Yeah, I could have copied my sorting code over, but I just did this as a quick hack. Wow, this is actually showing that it thinks that account tenure and unfriend per month are strongly related, which I don't really see. But then here we've got these negative weights. So these are like it's got this version with these two together, and then this version with them negatively correlated, which is kind of what PCA is telling you about where the interesting relationships and differences are. So, well, this is not exactly the same order. I'd have to like move up account tenure and unfriend per month, but this is still pretty good. So I think that pretty much was, I accomplished my goal, which was to do a quick live hack where I added PCA to the Fighting Churn with Data framework. So if you were ever wondering, how to recreate that example, I should going back to my slide deck. So this example is actually in the book in chapter 6. But I don't actually give the code to do it. So now for the first time, I've basically redone that analysis on the simulated data set. So that actually, I think, brings me to the end of today's stream, pretty much, unless anyone has any other questions. Summary, what did we talk about today? Fighting churn is about targeted interventions, improvement, engagement, and support. What dislikes is 0.9 correlated with? I don't think dislikes was 0.9 correlated with anything. Let's see. Dislikes, I think, was pretty weakly correlated with stuff. Let me go back to that. This is the toy problem. Wait, no. I don't need to go through this. I should show you, I believe I have the correlation matrix open. Sorry for making y'all dizzy. Don't I have the correlation matrix open? Yeah, I have the ordered correlation matrix right here. So dislikes was not 0.9 correlated. Like more 0.4, 0.5 correlation. It has a 1 correlation with itself. And Algebra 97. Are there other dimension reduction algorithms that provide better results than PCA, or it's more problem dimension? It depends what you mean by better results. Because remember, PCA extracts the maximum information or variance. So the PCA, better is all relative. So I think hierarchical clustering is very intuitive. PCA is the most advanced. There is actually one other option that I thought was interesting. It's called simple component analysis. And it's actually like a hybrid of PCA. And it's not a very well-known algorithm. I read it once and I liked it. Simple component analysis. There is an algorithm. Yeah, this is actually the paper I read. So this is actually a good other one. Simple component analysis is like a hybrid of hierarchical clustering and PCA. It kind of takes the best of both worlds. So I would actually recommend this for those of you who are really, academically minded and want another algorithm. Okay, Strawberry Jesus 11. In the last matrix we did, dislikes had you mean in the weight matrix? Oh, okay, so dislike, what this is saying, dislike gets a very strong 0.9 weight by itself. So I think the interpretation here is that the fourth component resulting from the data is very strongly just made up of dislikes. So I haven't really tried to interpret all these components. So the fourth component is basically the dislike component. The second component is the message and reply component. These two are both account tenure and unfriend. This is the average of account tenure and unfriend. And this is the difference between account tenures, this component here. This component, is basically practically just the dislike component. And this component is the difference between the average of ad views, likes, and posts and new friends. And what does that mean? What is the difference between the average of ad view, like, and posts and new friends? So this message is high when someone has a lot of these metrics and very few new friends. That's interesting. So people who post a lot but don't have a lot of new friends are represented by component 5, which is interesting, but very hard to explain. And what I'm going to show in the next stream is ways to capture interesting relationships like that without these really uninterpretable, loading matrices. Okay, so back to the summary. Fighting churn is about targeted interventions like improving your product, engaging with your customers, or giving them support. Metrics summarize customer events and also the subscriptions. The account tenure is an example of a subscription-based metric because it represents the time to the start of the subscription. Metric cohorts show churn versus behavior and are easy to understand and actionable. And that's why I like doing those visualizations and not just regression and machine learning. Although don't worry, regression and machine learning does come in later streams and later on in the book. Correlation is the strength of the relationship between behaviors. And you can look at correlation in matrices, correlation matrix, and scatter plots. I recommend preventing information overload by merging highly correlated metrics as averages. And we looked at how to do that with a loading matrix. So a loading matrix efficiently merges metrics using matrix multiplication. Hey Scott, have a good week. Thanks for joining. Nice to see you today. And lastly, hierarchical clustering finds correlated groups and is more interpretable than principal component analysis, which is basically what we've been talking about. All right, new year, new schedule. This is when I stream. I'm now only streaming once a weekend. I've got another project I'm doing with Manning, which is to make a live project with real data that you can practice churn analysis on. So I've got another project that I'm doing and I've got to do that on the weekend too, because I have a day job. So I'm only doing one stream a weekend now. I'm trying to do 2 p.m. That's my new stream time. Also, all my streams are now on a YouTube channel. So if you miss anything, you want to see my old streams, or of course they're all on Twitch too, and you're all Twitch watchers, so I don't know that I'm talking to you right now. But anyway, if YouTube is convenient for you, it's on YouTube now too. Again, this is where you can get the book, and there's your 40% off discount code, TWITGOLD40, and that's to get it from Manning.com books, Fight Churn With Data. Also, you can get it on Amazon, so if you have free shipping, you can get your free shipping, but then no discount code. 2 p.m. Pacific time, that is when I stream. I'll show that in 1 second. This is how to connect with me. If you want to connect with me on LinkedIn, just tell me you're interested in churn and we can connect. Please also follow me on Twitter. That's where I'll give you updates about the stream, about data science, churn, a lot of stuff about subscription businesses too. And the time, yes, 2 p.m. Pacific, and conveniently, here I'm telling you, that will be 2300 Central Europe, 5 p.m. Eastern, or maybe even 9 a.m. Australia, if anyone out there watches from Australia. Now, I have really had viewers from Australia. Max Payne Life, are you out there? I know some people from Australia watch me from time to time, so I'd like to get those times up there. But that's it. Thank you for joining. Really pleasure having you guys here today and asking the great questions that you asked. Makes the stream much more interesting and interactive for everyone. And on the video on demand, people will actually get hopefully their questions answered, because whatever is unclear for you will hopefully be unclear for whoever watches this some other time. So, bye-bye everyone. Thanks for joining. Have a good rest of your weekend. I'm actually going to get out there now. It's still sunny here in California. It's a little bit cool and crisp. I'm going to take my dog for a walk. He's been patiently waiting by the window for me to finish live streaming and get the hell out there. So, take care, everyone. Have good weekends. Happy data science. 11 p.m. for you, so you're in the Europe. But nice having you. Hopefully you can come back next week. Bye-bye.